by discussing this quantity called characteristic impedance. And as you can see, we are calling it Z naught, characteristic impedance, and it's going to be the ratio of our quantity V0 plus to I0 plus. And we talked about the origin of those terms last time we did a number of things. We took our telegrapher equations 1 and 2 from our transmission line model, and it's a first order ordinary differential equation system of solutions. These two equations are coupled because V and I appears in both. And if we were to look at this as a mathematical problem, we can solve for voltage or current by taking the derivative of one of the equations and plugging in the other. And if you do that for, say, the voltage, you get a second order ordinary differential equation in the voltage, and the proportionality constant is this gamma squared, and gamma has your transmission line parameters in it, R prime, L prime, G prime, and C prime. It has your frequency omega in it, 2 pi times the frequency. Gamma itself is a complex number which we can break out into a real part alpha and an imaginary part beta. So we also have a second order ordinary differential equation in the current. Looks the same. Proportionality constant is gamma squared also. So if we have a single second order ordinary differential equation, say in the voltage, and it's homogeneous, then it has a general solution, which is, well, if it's second order, the general solution is composed of two linearly independent solutions, and you can choose any two linearly independent solutions as long as each one of those solutions satisfies the differential equation and the boundary conditions. We have the differential equation. We haven't talked about the boundary conditions yet. We will see that these constants V0 plus and V0 minus, those will be determined by the boundary conditions. We're going to put something on one side of the transmission line and something on the other side of the transmission line. So when you have a transmission line, you're trying to get information from point A to point B. Typically you have a transmitter on one side and a receiver on the other side. And those will be our boundary conditions. Okay. We can write a similar equation. So voltage is V0 plus e to the minus gamma z plus V0 minus e to the plus gamma z. And we can write a similar equation for the current. Since we have the voltage, we can take the first telegrapher equation and just plug in the derivative of the voltage and then write a similar expression for the current. And that's what we did last time. You can see that the current I of z is I0 plus e to the minus gamma z plus I0 minus e to the plus gamma z. It has the same form. I0 plus and I0 minus are related to the voltage. So gamma V0 plus over R prime plus J omega L prime is what we define to be I0 plus, and minus gamma V0 minus over R prime plus J omega L prime is what we define to be I0 minus. So just looking at this collection of symbols, we can write the ratio of V0 plus to I0 plus and give that a name. And it turns out this is how we characterize the impedance of the whole transmission line. So the transmission line as an entity is characterized by an impedance, and it is V0 plus over I0 plus and Z naught. And so if you take that ratio V0 plus to I0 plus, you get R prime plus J omega L prime over gamma. and plugging in for gamma as the square root of r prime plus j omega L prime times g prime plus j omega C prime, and do the algebra, you get that the characteristic impedance is that. Note that the characteristic impedance is r prime plus j omega L prime over gamma, and that appears here also, r prime plus j omega L prime divided by gamma. So the characteristic impedance is also minus V0 minus over I0 minus. Okay, so ratio of these constants. All right. Any questions on what we did last time? All right, so we're going to take a look at this, or we're going to take a look at these set of equations and try to make some physical sense out of what it is we're looking at. And one way to do that is to take a look at some special cases. So let's start today by looking at a special case of these equations, and the idea is I would like to see if I could understand these equations more physically. Let's take the special case of a lossless transmission line. Okay, so in the special case of a lossless transmission line, I'm going to go back to my transmission line model. Get past it, yeah, there we go. Here's our transmission line model. So we would say that the transmission line is lossless if this resistance per unit length is 0. It's an ideal case where your conductor has no resistance per unit length. It's made out of something better than gold or something better than copper, an idealized conductor. Okay? R prime is equal to 0. We would also say that this is a lossless transmission line if no current can flow from one conductor to the other, or if we can say that the insulator is perfectly insulating, or that G prime is equal to 0. The admittance of this resistor is equal to 0, or this resistance is infinitely large. It appears as a perfect open circuit for that current. So if R prime is 0 and G prime is 0, that would represent sort of a lossless transmission. Okay, so let's take that as our special case. R prime equal to 0 and G prime equal to 0. Okay, in that case, we can start to look at these equations from that perspective. Let's take our parameter, one from last time, a couple from last time. So if we look at our complex propagation constant, so I copy it from last time and give you time to write it. So the complex propagation constant, gamma, we found that in general to be square root of r prime plus j omega L prime times g prime plus j omega C prime. And since it's a complex number, then we can write as alpha plus j times beta. So in the case of a lossless transmission line, we would have, so that would be the square roots of r prime is 0, so that's j omega L prime, And G prime is 0, so that's j omega C prime. So this is the square root of L prime times C prime, and then the two j omegas, you get just like j omega squared, you take one of the j omegas out. So that's square root of L prime times C prime. So that means that alpha is equal to 0, and beta is equal to omega square root of L prime times C prime. So the complex propagation constant is pure imaginary. In the case of a lossless transmission line. Which is why we say alpha is representative of the loss properties of the transmission line. That's why we call it the attenuation coefficient. And if there's no loss, then alpha is 0, no attenuation. The signal on one side traveling across the transmission line to the other side will not experience any attenuation, no loss, as it goes across the transmission line. Okay, beta, we will see, is going to be related to the wavelength as you propagate through the transmission line. Okay, we'll save that for a little bit later. How about the characteristic impedance? Well, the characteristic impedance, Z naught, there we have an expression, general expression, as the square root of R prime plus j omega L prime divided by G prime plus j omega C prime. So in the special case of a lossless transmission line, we have, what do we have? R prime is 0, G prime is 0, so this is square roots of L prime over C prime. Z naught is purely real. And in many real transmission lines that you would use in a lab or think about making yourself, you would want to make a transmission line with low loss, right? You would choose pretty good metals and pretty good insulators because you want the cable to function as a cable. And the spec on a typical transmission line is typically characterized by a real characteristic impedance. Those of you who have used coaxial cables before, does anybody know what's a typical characteristic impedance of a coaxial cable? 50 ohms. So you'll see 50 ohms is pretty typical, and so is 75 ohms. They're a little bit different. The 75 ohm coaxial cable will be a little bit more narrow, and we're going to actually see later when we derive inductance per unit length and capacitance per unit length that the geometrical parameters of the coaxial transmission line are important for determining its transmission line parameters and therefore its characteristic impedance. Okay, what about the voltage and the currents? So the voltage, last time we had up here, so V of Z is equal to V0 plus e to the minus gamma Z plus V0 minus e to the plus gamma Z. And in the special case of a lossless transmission line, you have V0 plus and gamma, so that is pure imaginary. So gamma is j e to the minus j, beta is omega square root of L prime C prime, plus V0 minus e to the plus j omega square root of L prime C prime. Or we would typically write this as V0 plus e to the minus j beta. You have a z, and z, plus V0 minus e to the plus j beta times z, where beta is omega square root of L prime times C prime. So in this description of the voltage, we have an explicit pure imaginary in the exponential, V0 plus e to the minus j beta z, and V0 minus e to the minus j beta z. Okay, do the same thing for the current I of z. So I of z, here's our I of z, this time. So I of z we found to be I0 plus e to the minus gamma z plus I0 minus e to the plus gamma z. So this is I0 plus gamma's pure imaginary. So the we have e to the minus j beta z again. And I0 minus e to the plus j beta z again. And we can write this in terms of the characteristic impedance in V0 plus. So I0 plus is V0 plus over Z naught, e to the minus j beta z. And I0 minus is minus V0 minus over Z naught, e to the plus j beta times z. So in terms of voltage and current, assuming we know our frequency and our transmission line parameters, then we know beta. And from L and C, you get Z naught. So if you're just looking at the voltage and the current, we're down to two unknowns. V0 plus and V0 minus are the two unknowns. So if we can determine V0 plus and V0 minus, then we have the problem completely solved. In order to get these last two parameters, we need two things. We need the boundary conditions. V0 plus we're going to see is going to be related to how much power we put on the transmission line. And then V0 minus we'll see is going to be related to the properties of the receiver that's attached to the transmission line. So let's march in the direction of seeing what that means from the point of view of visualizing in the time domain what these terms in the voltage and the current mean. So let's look at, let's go back to the time domain and get a visual image of these terms for the voltage and the current. So let me look at the first term separately from the second term, and then let's take a look at the time domain. So the first term of the voltage is V of z is equal to V0 plus e to the minus j beta z. So here we're going to suppose that V0 minus is equal to 0. and we could just isolate that one term. V of z is, V0 plus is in general a complex number, so let me break that constant into some magnitude and phase. That's V0 plus. And then I still have my e to the minus j beta times z. So here I'm writing V0 plus, which is a complex number, explicitly as having magnitude and phase. Okay, now, as you know from your homework, if you're in the frequency domain, or if you have this phasor, then we can go back to the time domain by multiplying the phasor by e to the j omega t, and then taking the real part. So let's do that. So v of z and t is going to be the real part of the voltage phasor times e to the j omega t. And so that's going to be the real part of the magnitude of V0 plus e to the j times the phase angle of V0 plus e to the minus j beta z e to the j omega times t. Okay, so the real part of that is magnitude of V0 plus times the cosine of omega t minus beta z plus this phase angle V0 plus. Okay, now that's something that we can plot. So let's plot v and z of t for, let's assume that this constant phase angle V0 plus is equal to 0. And let's assume that we're taking it at a time snapshot of 0. Then v of z and 0 is equal to the magnitude of V0 plus times the cosine of minus beta z. And cosine of a negative angle is the same thing as cosine of the positive angle. So this is magnitude of V0 plus cosine of beta times z. Okay, so if we were to take a snapshot of this wave at one particular value of time, time equal to 0, we would see that it looks like magnitude of V0 plus times the cosine of beta times z. So what does that look like? Grab this figure here. If I were to plot that on the z-axis, then, well, I've got a cosine, and we know what the cosine wave looks like, right? We can sketch that. And so on the horizontal axis here, I've got the z-axis, or the z-coordinate. And on the vertical axis, I have the y-axis, and I'm plotting the voltage, V of z, time equal to 0. And so physically, the magnitude of V0 plus represents the height of this wave. Okay? Magnitude of V0 plus. The magnitude of that V0 plus constant appears in front of the cosine, and that is the amplitude of the wave. And the lowest value of the wave is minus the magnitude of V0 plus. And the wave, as we would expect, is periodic. So this wave repeats. If we look at peak to peak, this wave is repeating every time the cosine repeats. Now the cosine is periodic in 2 pi. So when beta z is 2 pi, 4 pi, etc., then the wave just comes back to its initial value. So this point here, where it repeats again, is when beta z, so at this particular value of z, is equal to 2 pi. Okay. So z1 is equal to 2 pi divided by beta. Z1 now is the distance between peaks, and a better name for that is the wavelength. And we're going to use lambda to represent the wavelength of this wave. So when we compute beta, the pure imaginary part of the complex propagation constant, if you take 2 pi and divide by beta, you're getting the wavelength of that wave, periodic wavelength. Okay, now this was taken at some snapshot of the wave, and we can also talk about, let's say I am standing at z equal to 0, and I don't let time be stationary at t equal to 0, but I just let time go forward, as time usually does. What is this waveform doing as time becomes increasingly positive numbers? So if I look at this expression here, and I want to kind of visualize what this blue waveform is doing as time incessantly marches forward, what is this wave doing?
Is the frequency changing?
The frequency is constant.
Okay.
Yeah, so the frequency is well, we know that omega is 2 pi times the frequency, right? So the frequency is omega divided by 2 pi. It's a constant. And 1 over the frequency, or the inverse of the frequency, is the period, time period t. Okay, so that's a constant. Someone, what is this wave doing?
Will it continue to propagate?
It continues to propagate. That's right. This waveform, as t is increasing the phase inside of the cosine, and as time is increasing, then, so if I pick some phase point here, as time is increasing, in order to keep that point of constant phase, z has to increase for this quantity to be the same. So this whole waveform is traveling to the right. Imagine this whole cosine translating to the right. So we would call this a traveling, example of a traveling wave. Well, if it's a traveling wave, how fast is it traveling? If I'm sitting at some point here at z equal to 0, then, and I watch the wave go by, then I'm going to see a peak go by every period, 1 over the frequency. Right? So 1 over the frequency gives me some period, and if I wait a period, then another peak will go by. So the speed of this wave, or we would call it the phase velocity, this wave is traveling a distance lambda in time period t. And t is 1 over the frequency, so the phase velocity is lambda times the frequency. Phase velocity. Okay, the phase velocity, as you can see from our expressions for lambda and omega, lambda times the frequency is the phase velocity, so another expression for the phase velocity is going to be 2 pi divided by beta times the frequency, which is omega divided by 2 pi. So the phase velocity is also omega divided by beta. So in your expression for the voltage in the time domain, parameter omega and parameter beta, the ratio of omega to beta gives you the speed of the wave, phase velocity. Okay. Actually, let me move this up here so I can have some space. So let's circle that one because it tells us the physical meaning of the ratio of omega and beta. Okay. We will see something interesting. As an example, let's take a coaxial cable and let's suppose the insulator is air. So we have an air-filled coaxial cable. In that case, inside of your coax, if you look down at the coaxial cable, you will see inner conductor, air, outer conductor. Okay, so for the insulator, the permeability is 1, and the permittivity is 1. Permeability, we will see, characterizes the magnetic properties. It's non-magnetic. And epsilon r characterizes the dielectric properties, and the dielectric property of air is that it has a relative permittivity, or epsilon r, of 1. So these two numbers means we have air inside of our coax. There's a question? Yeah.
For the previous part, the derivation of the phase velocity, that's in the case of the lossless transmission mode, right?
Mm-hmm. Everything that we're doing here is lossless. Yeah. Something else happens when there's loss, and I'll let you do your homework for that one. Partially, I suppose. Okay, in the case when mu sub r is 1 and epsilon r is 1, you have an air-filled coax, then we're going to show that L prime and C prime, that product, is the same thing as mu naught, mu sub r, epsilon naught, epsilon r, and if mu r and epsilon r are both 1, this is the same as mu naught, epsilon naught. And so the phase velocity is phase velocity is 1 over the square root of L prime times C prime, which is the same as the square root of mu naught epsilon naught. And this is actually a number that you can calculate. Let me put in an intermediate calculation here. Phase velocity we just found to be omega over beta, and beta is omega square root of L prime C prime, so let me throw in that intermediate calculation. Omega over beta, and beta is omega square root of L prime C prime, so that the phase velocity is 1 over square root of L prime C prime, and L prime C prime we will show later in the course is the same as mu naught epsilon naught, and as you know from your homework, mu naught and epsilon naught are fundamental constants of nature. Mu naught is 4 pi e to the minus 7 henries per meter, and epsilon naught is 8.854 e to the minus 12 farads per meter. Has anybody made this calculation before? 1 over the square root of those two fundamental constants of nature.
I haven't made it before, but I know what it is.
What is it?
It's the speed of light.
Speed of light, yeah. So this is c, 3 e to the 8 meters per second. What does that mean? If you have air in your coaxial cable, then the energy in the coaxial cable is moving at the speed of light, 3 e to the 8th meters per second. Well, if I were to make a communication system, I would probably want to use that to move my information around. And that's why we use cables, and you can even use cables without metals at much higher frequencies, and that's the technology of fiber optics. You use the fastest thing around, speed of light, to move your information around. 3 e to the 8th meters per second. So this wave, right, we'd have a hard time taking a picture of it, but here on a sheet of paper we can draw what it looks like. But believe it or not, this is what the wave looks like. This is what light looks like. It has an amplitude and a phase, and if it's light from a laser, for example, the light will have a waveform that looks like this. All right. Any questions on our physical picture of our waves? We just looked at the first term of V of z, right? The first term of V of z is V0 plus e to the minus j beta z, and that was this equation here. If this first term represents a traveling wave, what do you think would be the difference of this second term? So it's got a constant and it's got a different sign in the exponential. We got V0 minus, that's a constant, and e to the plus j beta z. Someone, from what we just learned, physically, if this is a traveling wave as we just described, what might this wave here, that term there, represent? Yeah. That other wave is a traveling wave, but it is moving in the opposite direction. Okay? Because you have a sign change. You would have in your voltage time domain equation, you would have a plus sign sitting right there. And that means if t is increasing in time as it incessantly does, then z has to decrease for that phase to be the same. So to follow any point on that waveform, you have to decrease z. This whole wave is moving to the left. So the first term in our voltage phasor, let me copy that. So physically, we have V of z equal to V0 plus e to the minus j beta z plus V0 minus e to the plus j beta z. And this first term, V0 plus e to the minus j beta z, represents a traveling wave in the plus z direction. And the second term represents a traveling wave in the minus z direction. Okay, so somebody, if you have one wave moving in the plus z direction and it's a traveling wave, and you have another wave moving in the opposite direction, what kind of wave do you have when you add those two waves together? Let's say that the amplitudes are the same. Two waves moving in opposite directions with the same amplitude. What kind of wave is that? Standing wave. Yeah. So two traveling waves, one wave moving in the plus z direction, another wave moving in the minus z direction, will add constructively and destructively, and the result will be a standing wave. So the voltage expression that we have here really represents a standing wave. Okay. So these are standing wave solutions in the same kind of way that you have standing waves on a guitar string. You have standing waves of voltage on your transmission line. So V of z represents standing wave. And you can get all kinds of standing waves depending on the ratio of V0 plus to V0 minus. In fact, if V0 minus is equal to 0, that's a pure traveling wave. And if V0 minus is the same as V0 plus, if the magnitudes are the same, it is a pure standing wave. Okay, any questions on what all this means physically? So far, so good? All right, so now, to solve this problem completely, we need to find V0 plus and V0 minus. And to get V0 plus and V0 minus, we have to put something on the end of the transmission line. So let's terminate one side at a time and talk about a terminated lossless transmission. Okay, well, what does that look like? Let's see if I've got a picture of it. Yeah. Okay, so this is going to be a diagram that we use quite a bit for the next couple of weeks. Okay. It is going to be our cartoon of a transmission line, which is going to be, so we're going to say it's sort of infinitely long on one side of the transmission line. And then we've got the transmission line itself, Z naught, and then we're going to, bring in an impedance and terminate the transmission line. So you have your transmission line, and then we're going to, terminate the transmission line with the load impedance here. Okay? And that load impedance can represent, for example, the input impedance of a receiver. So on one side, I have my signal coming in from my source of communication. And then, so this is like your DirecTV antenna. And then this is that black coaxial cable coming from the roof. And then your box on top of your TV has an input impedance of ZL. ZL. The input impedance of that receiver. So, we're going to put our Z coordinate along the transmission line, and we're going to do something a little bit unusual here. We're going to put the negative axes of Z on the transmission line. So we're going to put the origin at the termination where the load impedance is, and positive Z axis is over here, and negative Z axis is over here. Why do we put the negative axis on the coaxial cable? Well, your book does it that way. And if we were to put the positive Z-axis over there, we'd have a lot of sign changes throughout the chapter. So to be consistent with your text, we're going to put the negative axis on the coaxial cable and the origin at the load impedance. That's a completely arbitrary choice where to put your coordinate system. Okay, negative Z is on your transmission line. The origin is at the load impedance. And actually, it's not a bad choice, we'll see. It's actually kind of convenient to do it that way. Okay, so the way to think about this is you've got a wave coming in on your transmission line. There's your wave. And let's say that's the V0 plus e to the minus j beta z term. And then, depending on the value of the load impedance, you're going to get some kind of back reflection. And that will be that minus z term, a minus z traveling wave. Physically, that's how you can think about it. You have some input wave on the left, and depending on the value of ZL relative to Z naught, you're going to get some kind of reflection. It's a wave, right? And if it sees a impedance mismatch, or we would call that some kind of obstacle there, then waves tend to bounce back and produce a reflection. And the amount of reflection is going to depend on the value of ZL relative to Z naught. So let's see that. We can solve for the reflection by defining at this node here. Let me say that I have some current at the load. So the current I at Z equal to 0 is going to be my load current. And then across my load impedance, I'm going to have some voltage across that load impedance, and that's the voltage at Z equal to 0. Okay, so V of Z, we know, is V0 plus e to the minus j beta Z plus V0 minus e to the plus j beta times Z. And I of Z, we know, is V0 plus over Z naught, e to the minus j beta Z, minus V0 minus over Z naught, e to the plus j beta Z. Okay, we just derived that. And we have the new first boundary condition is that the voltage at Z equal to 0 is the current at Z equal to 0 multiplied by this load impedance. So the load impedance is V of 0 divided by I of 0. And so that is V0 plus V0 minus divided by I of 0 is V0 plus over Z naught minus V0 minus over Z naught. Okay, so I can solve for V0 minus divided by V0 plus, and my algebra says that this is Z load minus Z naught divided by Z load plus Z naught. Okay, the ratio of V0 minus to V0 plus is ZL minus Z naught over ZL plus Z naught. Since this gives you the amount of reflection given some V0 plus, we're going to define this to be a parameter gamma. And gamma is going to be called your voltage reflection coefficient, or reflection coefficient. So if you know ZL and you know Z naught, you can calculate the amount of reflection that you're going to get on your transmission line, and that's calculated from this reflection coefficient. Okay, it's 8:55, so we'll pick up here on Wednesday, right? Holiday on Monday, so we'll see you on Wednesday. I'll post homework number 2. Homework number 2 due next Friday. Have a good weekend.